Thank you very much for your company and welcome again to your channel Transmission Lines Engineering TV. On this occasion, we will talk about the historical development of the evolution of the design methods for transmission lines. How the basic concepts were born as a theory for its implementation. So let's remember that at the end of the 19th century and early 20th century, when this industry was in its infancy, there were no books, no calculation guides or specifications which regulate the design and construction and operation of the electrical systems. Well, this video is all about that. How the theory was developed to design a transmission line, and as we know, a transmission line requires many calculations that go from the mechanical calculations of the cable to the design of very specialized structures, such as, for example, a phase transposition tower, or maybe a tower for a transition underground overhead. However, regardless of the complexity of the project, the basic components for the design of a transmission lines are as follows. First, we have the mechanical calculation of the cables, or calculation of the catenary. That is, the calculation of the curvature taken or shaped by the cable at different loading conditions. We have as well the calculation of the Rollin Span. And as a third place, we have the calculation of sags and tensions. These are basically the concepts that are the most basic ones for many locations. These concepts sometimes they slip past without knowing what they are and leaving the work directly to the software. However, it is very important to become familiar with these kind of concepts to have a better understanding of how modern software work, to know exactly what input to get into this software and what results to expect from them. The mechanical behavior of a cable obeys to the principle of temperature variation on the body. At higher temperatures, the molecules of a body tend to get apart from each other, which produces an elongation of the material, and with it decreases the attraction force between them of the molecules, which makes it a translation, mechanically speaking, on a decrease of the actual tension on the cable. Now, on the other hand, by decreasing the temperature of the bodies, the molecules will try to approach to each other, producing a contraction of the material. In this case, the force of attraction between the molecules will try to increase, and in mechanical terms, an increase in the actual tension of the cable will result. That's nothing else than a simple physical behavior of matter to which it obeys not only cables or as solid bodies, but also gases, electrical energy, thermodynamics, etc. The mechanical calculation of the cable, mathematically speaking, is based on the principle called change of state equation, which will be described in video A1-7, if I remember correctly. By the moment, we just will talk about its origins. The first change of state equation dates back to the year 1662 with the Irish physicist Robert Boyle, who performed experiments in a J-shaped tube in which he inserted mercury and discovered for the first time the behavior of a volume of gas in relationship with its pressure on it. This is known as the Boyle Law, and this law was based on a linear variation. Later on, other versions of the change of state equation were developed for different applications, such as the Gay-Lussac law in 1787, when the French physicist Jacques Charles discovered how gases vary their volume as a function of the temperature. Later, the Dalton law will come up based on the partial pressures in 1801, which deals with the sum of pressures that will be something analogous to the addition of tensions in the different layers of the cable that will be the precursor of the model known today as finite element. In 1834, we'll count the French engineer and physicist Benoit Paul Émile Clapeyron, who combined this Boyle Law with the Gay-Lussac law to develop the ideal gas law. The aforementioned equations, among others that were developed for other applications, deal with the relationship between volume, temperature, and pressure, which can be translated from a thermal system to a mechanical system, such as the thermal properties of the cable, the thermal expansion coefficient, and in parallel with the mechanical properties of the cable, what it means, the elasticity moduli, and with the same temperature as well, and the force applied on the cable. In this way, these change of state equations for thermodynamic applications represent the basis for the change of state equations for mechanical purposes, which means the mechanical behavior of the cable. The change of state equation is based on a third-degree equation, or a cubic equation, which has a complex root, a complex or imaginary number, a negative root as well, and another positive real root, which represents the value of the cable axial force in question. So the development of the cubic state change of state equation dates back to late 19th century, around 1880, when the German physicist Johannes Dietrich van der Waals developed the first change of state equation of cubic degree for various of the behaviors of the gases, which show that the gases do not really obey the ideal gas law of Émile Clapeyron, as it was believed, but gases follow a non-linear behavior that affected by other variables. So this is the reason why both transmission lines and other disciplines follow a non-linear analysis methods nowadays. At the beginning of the 20th century, it was observed that in the first transmission lines, it was generated accumulations of ice on the conductors, causing a sag increase, and therefore more frequent ground faults or faults between conductors were encountered. At that time, the concept of ice overload on conductors was discovered and developed as well. In 1913, V.H. Grazer carried out the first studies to investigate in detail the ice overload effects on the cable sag by means of observing a line in the vicinity of Spokane, Washington, United States, because in low temperatures conditions and accumulations of frost and fog, the line constantly went out from service, making it practically useless. Subsequent to the investigations of B.H. Grazer, other investigations were carried out in the transmission line Wallen-Paupack to Siegfried, and this one was a transmission lines in the vicinity of Pennsylvania, United States, by Mr. E.S. Haley and A.J. Wright, who discovered that in addition to the effect of ice on conductors, the elastic properties of the cable directly influence on the sag determination. In 1931, James S. Martin developed for the first time loading maps and assembling reference tables to define the calculation constants for each span length and the cable weight and mechanical tension for the application of its model of change of state equation, which pretty much had a very acceptable results, very good approximations. In this model, it was when the catenary curve was adopted to calculate the curvature of the cable in a transmission line. Later, by 1935, S. Noda and S. Nishiyama developed another mathematical model for the change of state equation. However, this model was never accepted because it was based on the fact that the weight of the suspension assemblies, as well as the elastic properties of the conductors, were negligible for any span length between structures, which history, of course, has proven that this principle is false. Another error in this model was the assumption that the mechanical tension on the suspension assembly was perfectly perpendicular to the hardware assembly, which it's also false, since it is currently known that the cable develops an angle with respect to the assemblies, which creates a vertical and horizontal component. So these erroneous assumptions caused the model become rejected. Now, have you ever seen the movie A Beautiful Mind, starred by Russell Crowe? Crowe personifies the American mathematician John Nash, who everyone saw him as a weird and crazy guy. It turns out to be that in 1945, John Nash and his son John Nash Jr. developed another model of the calculation, taking various models based on the difference of temperatures, elastic properties of the conductor, as well as the ice overloads, but added a new factor which influences in the calculation of the conductor sag: the thermal expansion coefficient, which it's a value for each conductor type. And in this way, it was possible to calculate how the temperature variation influences individually for each conductor type based on the concept called Rollin Span. I remember when I saw this movie for the first time, which I certainly love this movie, I never imagined that this character had anything to do with the development of the basic theory for transmission lines design. Now, on the other hand, the Rollin Span concept was introduced in 1924 by Mr. E.S. Thayer, who was an electrical engineer from Seattle, Washington, in the United States. This method is based on the fact that a multi-span line can be reduced by its equivalent span, which sag calculation and tensions will be valid for each span that makes up the cable string tension. It is equivalent to an electrical circuit composed by several resistors, which are reduced to an equivalent resistance to calculate voltage and ampacity. By mid the 50s decade, the change of state equation was adopted as we know it today, and we will talk about it in another video. Parallel to the development of the mathematical model that was sufficiently precise for the mechanical calculation of cables, it was necessary as well to develop a technique to locate the structures throughout the alignment of the line, which sometimes had very variable geography. First, it began with the criteria of locating the structures in a uniform manner, that is, maintaining a uniform span. However, the designers realized that for the same curvature of the cable catenary, it was not possible to maintain this uniformity since it presented ground clearances problems. By early 1930s, the concept of constructing the catenary was introduced based on the mechanical calculation on an acrylic template, and parallel to this one, it was drawn a second catenary simulating the required clearance to the ground. The result was the first structure's location template. This idea became the tool that even today continues to be the accepted method for structure spotting, on which modern softwares for structures locations are developed. Further on, by 1960s, when the structures began to be manufactured in different sizes, a variant to the development of this template of the construction was made on the acrylic template, because they were added more parallel curves to simulate the different heights of the structures, and in this way it was possible to adjust the extension of the catenary to the topographical needs for each project, and making it possible for different location options to evaluate the most economical option, reducing the amount of structures, construction time, and maintenance as well. Another interesting topic that contains a great history is the analysis of AOLM vibration on cables. Today we have available a variety of shock absorbers for different types of cables and different applications depending on wind speeds. In 1947, Tom Patterson had the vision to find the way in which the vibrations of the cable under low and laminar winds produce a fatigue effect on the conductor's wires, especially on tangent structures. This fatigue effect appears when the external wires of the conductor are permanently attached to the attachment clamps, so that the constant movement causes a weakening of the outer layers of the wire, resulting in the mechanical breakdown of the conductor. So, in order to eliminate this problem, Tom Patterson developed a system of additional stranded wires around the main conductor in the tangent clamps, and in this way the additional stranding will be the one that suffers the fatigue damages and not the main conductor. The only thing which will be necessary is a bigger tangent clamp, and replace of course the additional damaged strandings. This attachment was named as damper, which would later raise an entire industry for sales and technology development to prevent mechanical damages on cables against the effects of AOLM vibrations on them. On the other hand, grounding systems are another key component for the good design and safe operation of a transmission line, which also have its history. The first ground systems were discovered in 1836 by the German scientist Carl August Steinhill, who discovered that the soil could be used as an electrical conductor. Later, in 1861, the use of grounding systems for applications in the telegraph lines were extended, but the effect exerted by the soil in dry conditions were discovered, resulting in the discovery of higher impedances for the first systems to reduce the soil resistivity by means of water. So in 1883, communications technology appeared using also these grounding systems. So the application of the grounding systems were used almost from its early beginnings by Nikola Tesla, precisely to drain the voltage of overloads that were generated by these systems based on alternating current, which required the system that could eliminate the excess due to the overloads and maintain public safety, and in this way win the battle against Thomas Alva Edison and the direct current system. Finally, one of the cables that are part of the massive grounding system of a line is the so-called shield wire, which connects all the structures to ground by means of a resistance circuit in parallel. In 1977, it was released the very famous optical fiber grounding wire, OPGW, which takes the advantage of the overhead shield wire, and it's inside its core. It contains a tube with optical fibers, allowing transmission lines not only have the application of transporting electrical energy, but also to provide them the ability to be used as communication systems as well. So in 1980s, this fiber optic OPGW had its first great boom as means of media of communications, and today is a fundamental part of a transmission line industry. So as you can see, every industry has its evolution history in terms of design theory and mathematical models for its practical applications. In my opinion, I believe that this story has been forgotten, and we use the calculation principles, the materials, and calculation softwares without holding up to think about those characters who invested a great part of their lives to investigate the phenomena and interpret them in a mathematical model of easy application. So one of the purposes of this channel, Transmission Lines Engineering TV, is precisely that, to bring this concept back so they continue alive and valid. Because perhaps within the audience there are people who might be interested in becoming involved in research and further improve the design techniques. So thank you very much for your kind visit. Don't forget to subscribe and leave me your comments on this video. So on the next video, Transmission Lines Engineering TV, training to power the world.